Okay, we're very, very pleased to welcome Lou back, who's going to talk about ER equals E something R. Is that right?
Something like that. ER equals EPR. Yeah. EPR. Entanglement.
Okay. Yeah.
Okay.
Good.
Shall I begin? Let's see. First of all, there's a technical point that I'm not going to go into in this talk, which you might be interested in about, which is called quantum monogamy. It has to do with measuring how much entanglement can be shared by 3 different qubits. And I found a paper that I think is readable, and I put it in the chat line here in case you want to look at it. The other papers in this subject, there are lots of them. You can look up Leonard Susskind. Let me type that in the chat line just in case you don't know the spelling. Leonard Susskind, physicist who has written many papers about the possibility that entanglement would be associated with spatial connectivity, and in particular that quantum states that are entangled should be connected by a wormhole. That is his idea, thereby interrelating general relativity and rather far out properties of general relativity with quantum theory. So that's the theme of this talk. And I'm not giving you references to Susskind and so on because it will be very easy for you, if you're interested, to either do that or to put in the slogan, his slogan, ER equals EPR. Oops. ER equals EPR, which means Einstein-Rosen in the first case and Einstein-Podolsky-Rosen in the second. They wrote papers around the same year. Einstein-Rosen about the possibility of a wormhole between 2 points in space, and EPR about the curious properties of non-locality in quantum mechanics, which they hoped showed that quantum mechanics was incomplete at that time. So Susskind uses that slogan to suggest that indeed quantum entanglement might be a kind of geometric connection. Now I want to begin. Let me see here. Yes, share sound. I want to begin by talking about some kind of physical connectivity that is very geometric and ordinary physical theory, not quantum theory, by showing you a short video from Physics Girl.
Check this out. I'm just gonna drag this plate through the water in the pool. That's it, but look what forms. Perfect black circles on the bottom of the pool. And it's so weird, they don't die. They just keep going right next to each other. I sped this footage up because the circles took 3 minutes to cross the pool and didn't seem to be dying out. These got sharper as they went and made it all the way across. So cool. And look closer, you can see what's causing them. There are 2 almost unnoticeable dips in the surface of the water. Why don't they die out? And how do these dark spots form? And why do the dips move together? So many questions. Let's first look at what they are. When I dragged the plate through the water, you could see it forming little vortices like you get when you move a paddle through the water. A vortex is a gas or liquid moving in circles with what we call a vortex line going up through the circles. They are everywhere. Tornadoes, water flowing down the drain, hurricanes, or the movement of air over an airplane wing. Vortices often form when there's a difference in fluid speed, like fast wind moving over slow wind. As you move the plate forward, the water right next to the boundary moves with the plate because of friction. The water further out is not moving. It's that difference in velocity that causes a shear force and starts the water spinning. This is accentuated by the water in front of the plate being forced around the sides and the water behind the plate being sucked forward as the plate moves along. In this coherent vortex, our dips can travel much further across the pool than a ripple without dissipating. Why? The vortex wants to keep its angular momentum, so it continues spinning as it moves through the water and only loses some energy through friction to the surrounding stationary water. So what we appear to have here is two vortices moving across the pool, but it seems weird that they stay right together. Well, when we create this vortex, we're forcing water to move around the whole plate, not just on the surface of the water. Our vortex line is curved. We're creating a half vortex ring. You know, like a smoke ring, bubble ring, or even the plume rising up from an explosion, but half of that. These two dips on the water's surface are just the ends of the half ring. They're connected, and that's why they stay together. We can see this if we put a little food coloring into the ends. The food coloring travels from one end to the other, and you can see the entire half ring. So cool! We just made a bubble ring without the bubble. This also tells you something interesting. The half ring is not a wave. A wave is a disturbance moving through a medium that transfers energy but doesn't transfer matter. When we added food coloring, we saw clearly that the vortex is transferring matter just like a smoke ring does. So sadly, it's not a wave. It's cooler than a wave. Now back to this half ring vortex. Isn't it weird? You've probably never seen half of a smoke ring before. Why? Well, according to Helmholtz law, a vortex line cannot start or end in a fluid, so a vortex line either wants to close into a loop or end at a boundary. If you tried to cut a smoke ring in half, it would either break up or, even cooler, it would break up into two smaller smoke rings.
I don't know if that happens. It would be awesome.
Since the line can't end in the fluid, it ends at the surface. You almost never see these half vortices though, because they have to occur on the boundary of two media. If you can think of another way to make the entire half ring visible, like a smoke ring or a bubble ring, let me know. So now, why does our vortex create those cool dark spots?
Well, the balance between gravity, centripetal forces, and surface tension creates a funnel shape which acts like a lens.
Lenses often work by focusing light to a point, like this Fresnel lens, which can melt pennies in the sun, but I digress. Our vortex lenses focus the sunlight away from the center, like so, and you have a bright ring surrounding a dark circle. The ring highlights the dark circle further, and you get these incredibly clear black spots. So cool! Now, I highly recommend trying this at home, especially if it's too cold to swim in the pool. Here are some tips. The water has to be very still. Even a small breeze makes it harder to create these. The sun has to be out, or it won't work. And you can try some other really cool things. Send your vortices at a wall. You'll see the dark spots spread out. Or try colliding two of them. Happy physicsing!
Right. So you understand the analogy that I'm making, that you might think of a wormhole between, or the two black holes with a wormhole between them as an analog of the Flacco-Soliton, as she talks about it. It gives you a picture to think about, and if you like her web experiments, let me see. Just trying to get the ability to manipulate my own computer here. Yes. Okay. You will also find that, oops. Nope. Well, I will tell you that you will also, I see what happened. Just one moment. I did want to show you this reference. So if you look up Flacco-Solitons physics girl, Flacco-Solitons, then you will see some other videos of hers. And this one surprised me enough to just show you quickly a little of it, not the whole thing. She's doing the same experiment. Let me just stop it. Stop it. There, doing the same experiment. If you don't own a swimming pool, you could do this experiment in your kitchen. You see, now the plate is a spoon and the swimming pool is just a large container of water. And she manages to get the experiment to occur right there just as well. And so this reminds me of a few years ago when we were trying this at the Oberwolfach in the sink in one of the seminar rooms, but we didn't have good lighting. So this video inspires me to try again to do this experiment. Well, that's for your experiments, and I won't do any more. Question on that so far? Well, one question.
I wish it wasn't quite so cool.
You were getting tired of being told how cool it was?
Yes.
Well, yeah, sorry, but that I'm not the producer of those videos. They are advertising physics for people, right? Yeah, but anyway, it is cool. Another question you might ask is, did anybody do a job of writing down the mathematics of those vortices in water? And I'm not sure, this particular one where you have two vortices connected by a vortex tube with an interface like that. So you might look around to see if you can find a reference. I don't know one. Okay, so here's my slideshow, and what I want to begin with are some images from the web about this topic. So if you look around, you will see some of these images, which tell you a bit about the subject without reading any papers, and they'll give you an idea or two, and then you may use them as a guide to look at some of the papers if you're interested. So look at this image. The top of the image is indicating the ER part, a wormhole which is connecting two black holes. The left and the right sides are widely separated parts of space-time, presumably. And then the lower part is indicating an entangled state, where you have, and this up-down, you have to understand what this little up-down means. The up-down means that it's possible to observe the left particle on the left side, and it's possible to observe the right particle on the right side. And you don't have two of them. You just have the possibility of a left particle being observed on the left side and a right one on the right side. And then the two kinds of observation are: green up is observed, in which case violet down will have to be observed on the other side, and vice versa. But we don't know which. In the quantum situation, the complete information is green up, violet down, or green down, violet up, and we don't know which, but when an observation is made, one or the other will occur. And so they're correlated. If one is up, the other is down. And they can be widely separated. And in particular, one of them could be at the mouth of one black hole and the other at the other. So what mediates this kind of connection between things that are far apart is the question about quantum entanglement. And where would you get the suggestion that a wormhole should correspond to this kind of correlation? Well, I'm not going to tell you the whole story, but I'm going to give you some indication. And as I said at the beginning of the talk, I'm showing you some images that you would encounter on the web, and you'll encounter many images about this hypothesis because it's colorful. This is a nice one. Here you see the notion that you have two widely separated places in space. You'd have to go many, many light years to get from here to here. But on the other hand, the wormhole takes you directly over by that topological handle. And then this slide says the fabric of reality might be woven from quantum entanglement. Wormholes connecting two black holes in different parts of space-time can exist, but only if particles on the black hole's surface are quantum entangled. Break the entanglement, and the wormhole snaps too, suggesting entanglement is the thread that binds space-time together. Well, that's the theme, but these are very large-scale claims about the relationship between quantum theory and geometry, and you certainly don't want to take them as gospel. But why would someone think this way? That's part of the question. And other images. Artists' conceptions of the two particles being correlated and the wormhole. I can't hear that comment very well. Is that a comment, or is that just background noise? Background speaking. Okay. Now here's another idea that happens here. And as you know, there is this idea of Hawking radiation. Hawking radiation is the idea that, for example, a particle pair may occur out of the vacuum, outside the black hole, pair creation from the vacuum with sufficient energy. And then one element of the pair may be sucked into the black hole, and the result is that the other pair has appeared outside the black hole. The net result of that is actually that the black hole lost mass and that it appeared to radiate a particle, and that's called Hawking radiation. So the pair, the one that went into the black hole and the one that's outside, are entangled. They were produced together and they're entangled. And so in this suggestion, the pair and the one that's inside the black hole should be linked by a mini wormhole that goes from inside the black hole out to the Hawking radiation. So this is giving a geometric picture of the Hawking radiation as this enormous collection of wormhole hairs going out of the black hole into the outer space. And other associated ideas then occur to people. For example, you could imagine in a thought experiment all of the Hawking radiation collected up until it became so massive that it became a black hole, and then you would see a black hole and another black hole with a wormhole or many wormholes going between them. So that geometry is thought about and depicted colorfully by some artists in some articles. This is the same intent as this sketch, but drawn in a way that is pleasing to some. And then there is the matter of quantum information in relation to this idea. You could have a single Bell pair. Now that would be something like 2 qubits and representing spin up, spin down, correlated with spin down, spin up, just something very quantum. And then should that be a wormhole, or would it be that by having many of them, it would turn into a wormhole? So at what point does quantum correlation turn into a wormhole, if it does? Question. And then other things that you will see if you're looking at the images that people use is a new role for the perennial Necker cube. The Necker cube, here it is. If you look at one Necker cube, appears to be in 2 possible geometric states. It either appears to have this face here up and to the front, or down and to the back, just like this, up and to the front, or down and up and to the front, or down and to the back. And when you look at it, it tends to flip back and forth between the 2 states. But a thought experiment for you, are these Necker cubes entangled in your cognition? Can you look at one of them and have this go up and to the right while this one goes down and to the back? And you can, for a moment, I'm only reporting my own perception, I can for a small moment have them different, but it doesn't seem to be a very stable state of perception. They tend to get linked up with one another. Whether this has anything to do with quantum entanglement, I don't know, but it's a nice metaphor to think of. On the one hand, this represents superposition. All by itself, the Necker cube represents superposition, both or neither or and the Necker cubes together represent entanglement. And then this is an artwork that I made on my computer a long time ago, but I hadn't thought of it in terms of entanglement. I just had fun looking at this and seeing how they tended to correlate with one another. So as you see, you get strings of forwards or back, but when you look at one of them and you bring it forward, its neighbors tend to go forward and it spreads out in the network. Enough of that. So Susskind makes physical arguments that suggest that quantum entanglement and spatial connectivity are essentially related. A key instance is entangled particles across the event horizon of a black hole. And there's a multiplicity of ways of thinking about such entanglements. One way to think of them, a pair entangled like that, is that they traveled from a common point of production. That would be, for example, a common point of production outside the black hole, and then one of them got pulled in. And the connectivity is, of course, given. The space is connected. If it weren't possible to get in, then how could they become separated and entangled? But another way to think about them is via Hawking radiation, as I said, and possible tunneling across the event horizon. And in quantum tunneling, something goes from one place to another without apparently going through the intervening connecting space. If L and R are completely disjoint spaces, then a topologist would regard them as independent. You'll notice that if you think to your personal topologist, if somebody said to you, I have two disjoint spaces, just thinking in pure mathematics, then what you meant by that was that there was just no connection between them. Not only no topological connection, but they were just utterly independent of one another. No, that's not a physical statement. That's a mathematical notion that we could have entities that are completely independent of one another. We take that as more or less axiomatic in topology and mean that disconnection is that kind of independence. So the idea that disconnection means not correlated is kind of part of the meaning of what a disconnected space is. On the other hand, entanglement shouldn't be possible in a disconnected topology, as I just said. When there is a possible connection, then we can imagine an entanglement. So if you're thinking in that very abstract way, then it certainly does seem that entanglement and topological connection should be related to one another. On the other hand, this is a rough summary of the kind of argument that Susskind makes. Then I recommend you look at the papers or his videos. He has the following kind of thought experiment. There's a black hole, and here's its event horizon, and here's a particle outside the event horizon, and here's a particle inside the event horizon, and they are entangled with one another. So here are two particles that are entangled with one another. And then on the other hand, here's another black hole here's another event horizon far away. And these black holes are not necessarily connected with one another in this thought experiment. They're just sufficiently far away. No wormhole yet. And here's a point inside the event horizon of this one. And we will assume that that P prime and Q, these two inside the event horizons of these two black holes, that they're entangled with one another. Suppose there were entanglement between the two black holes. Well, then you arrive at a quantum information paradox if the two black holes are actually separated of the following sort. You have that P prime is entangled with P by assumption, and P prime is entangled with Q. So I meant P is entangled with Q and Q is entangled with P prime. I wrote it slightly wrong, but I have Q entangled with two other particles. If a given particle wants to be entangled with two other particles, there are severe restrictions on the way it can do that. The subject of that is called quantum monogamy. In a certain sense, to say it all too roughly, it can't be entangled with the other two. It can be entangled with two, but it's hard for that to happen. And if you assumed that it was sufficiently hard that it couldn't happen, then you would be in an information paradoxical situation, because these are very far apart, and yet you have entanglement between the two black holes. So his argument goes, if there is entanglement between the two black holes, that would be one entanglement, and yet it is natural and present that particles inside the black hole will be entangled across the event horizon. And that gives rise to a paradox unless there were a direct connection between Q and P prime. And so he takes the solution to this problem to be that there should be a wormhole from one black hole to the other to avoid the problem of quantum monogamy. That's a rough picture of his argument and why he thinks that black hole wormhole is related to entanglement. So have fun looking at the papers if you're interested. Now what? Yes.
Lou, can I just say, this monogamy of quantum, is this a statement that it's got to be true, or is there some evidence that it must be true? I mean.
This is part that's rigorous enough if you're just looking at quantum information and states the way we have been talking with each other privately about. The paper by Toner and the other person that I put in the chat line explains how you make certain entanglement measures for states of three particles, and how there are bounds on those entanglement measures that arise from the fact that you have three particles and you're trying to get them to be entangled. So you can't get the entanglement measures as high as you would between two.
Okay, so there's some mathematical justification for monogamy.
Yeah, that's right. That's right. Yeah. You can imagine it if you were to just start drawing some examples of entanglement. If you try to make for yourself a 3-qubit state that has as much entanglement as it can, and you'll see that in order for one particle to be entangled with the other two, you're kind of sharing things, right? You're sharing resources. It's just like in real life, but not the same. If you were not being monogamous, you would be sharing your resources in a way that might compromise you. And similarly with the quantum states.
Okay.
Anyway, that's a very sketchy picture of what these arguments are like, and they certainly aren't proofs that entanglement must be mediated by black holes, but they're suggestive. So now I want to talk about quantum states and tensor networks, and we'll come back to these themes as we go along. So let me now shift and remind you what is a tensor network. Tensor network, in my view, goes back to people like Roger Penrose, also Richard Feynman, who liked to draw diagrams of mathematical structures. But quite particularly, Penrose had the idea of drawing graphical diagrams that represented tensor-like expressions in his PhD thesis in the 1950s. And then later in some papers that he wrote and throughout his career. It's an artistic and mathematical endeavor. So instead of writing this tensor theta upper A, B, lower C, Penrose writes this nice blob with some lines sticking out of it like that. And those could be connected to other blobs and thereby form tensor expressions. With no connections to other blobs, you might have something like this: theta upper A, B, lower C, chi upper D, lower E, F, G becomes this little picture. But then tensors are contracted with one another. So here's a tensor in which we have a lower D and an upper D, and that means you would sum over the Ds. And that means that one of the lines coming from the theta, the D line, is connected to to an upper line coming from the chi, and they are connected here. So then you see that this tensor expression corresponds to a graph. And the nodes of the graph are these little pictures that you've drawn, and the edges of the graph, of course, are the indices of the tensor. So this gives you graphical expressions for your tensors. You may wish to take the graph and deform it into some other picture. You may wish to put these graphs in such a way that they look like morphisms in a category drawn geometrically. For example, Penrose probably was not thinking of this as an element of a category, but we in our indoctrination would look at this and think, yes, it must be some tensor category, and he has this 3 object going to a 1 object, and this other 1 is going up to a 3 through that morphism, and there seems to be a duality here, and so on. We're used to thinking that way, but it could just be a graph, and as a graph, it can still represent the contraction of the tensor. And these kinds of representations have become popular recently among physicists for doing lots of things, and they've been popular among graph theorists and statistical mechanics people for way longer than that. Now, it's useful to represent quantum states by tensor networks, and I'm going to show you how you do that in an example. So let's think about an entangled state. Here's a nice entangled state. And if you're not used to the notation, this means that I have a particle with 2 states, 0 and 1. And this represents 2 particles, as I said earlier, and it is the tensor product of their states. So when you write vertical slash some label bracket, it could be a single vector, could be a tensor product of vectors. In this case, 0, 1 means 0, the 0 vector, tensor the 1 vector, and this means the 1 vector, tensor the 0 vector. So there is a left factor, which is either 0 or 1, and there is a right factor, which is either 0 or 1. And if you make an observation of this state, you will get one of these or the other, so that if you make an observation, you don't know which you'll get, but if you got 0, then the right one would have to be 1. And if you got 1, the right one would have to be 0. Left and right can be thought of as 2 particles that were produced in some interaction and then separated until they were far apart. Say one of them is in Chicago and the other is in London. And with that, a measurement in Chicago would confirm for the person who measured in Chicago that the person in London would get a 1 if Chicago got a 0. But London doesn't know that until it makes the observation. But in this case, it's definite. If in Chicago you get a 0, then in London you'll get a 1. If in Chicago you get a 1, then in London you'll get a 0. You can have other situations where I measure in Chicago and get a something, and then that limits what could happen in London. So this is an example of entanglement. And depending on how you think about it, it seems either ordinary but probabilistic or mysterious and very quantum. And that's a matter of how you tend to think about it. The mysteriousness comes from the fact that you really do not know before you measure what it's going to be. So then it feels like when you measure, you somehow instantaneously cause something to happen in London. And it wasn't supposed to have been that way before you measured. You didn't know how it was before you measured. So there's a procedure that people invented, Charles Bennett, and I always forget the name of his collaborator, called teleportation. And in the teleportation procedure, we're going to start with a state. Let me use a different diagram, or use this diagram, or maybe even this diagram. I have a state here. This is in Chicago. I have an entangled pair which is spanning between Chicago and London. And I'm going to use the entangled pair to transmit to London an exact copy of the quantum state in Chicago. This is the teleportation procedure. You end up, of course, destroying the one that's in Chicago in order to get a state to appear in London. But it's not so simple. It goes like this. You make a measurement in Chicago of the tensor product of the state in Chicago with the left part of the entangled state. All right. Having made a measurement of that kind, you find that the new state that is the result, suppose this was, I should have made a slide showing you how it would go. If this was 0, 1, tensor 1, 0, plus 1, 0, and you saw 0, then there would be a 1. And this state psi would then look like that state psi and whatever the measurement did to it, tensored with the 1. And you would get a new state. The way it works out when you do the mathematics of it is as follows. The measurement corresponds to taking the coefficients of the state psi and multiplying them by a matrix, Mij, which is the result of doing the measurement, taking a certain linear combination. But that's also taking a linear combination and a matrix multiplication with the left-hand factors of the E. And so what happens over here is that you get a new state, which is the result of multiplying psi by M and then by E. That's what happens. The tensor network shows it to you very clearly, but of course you have to go through the quantum mechanics a little bit to see that the quantum mechanics is telling you that that's how it happens when you measure this tensor product here, that you would multiply by a certain, you would contract with a certain matrix, and you would contract the entangled state and end up over here. So what happens is that psi prime, when you do this, is the result of multiplying psi by a product of two matrices. So that's what Bennett and his collaborator understood, but probably not in diagrams. And then they said, so if we make the measurement in Chicago, we will get a new state that somebody could measure in London. But it won't be the state we started with. It'll be a new one multiplied by a matrix. But if we could tell the person in London which matrix it was, then they could multiply by the inverse of that matrix and get this state. Wait, what do you mean multiply by a matrix? Multiplying by a matrix isn't a quantum operation. But it could be. Quantum operations are unitary transformations. So if this matrix multiplication, if this EM is actually a unitary operation that was applied to psi, then we're in good shape because we can tell London, do that unitary operation with your quantum apparatus, and then you will have turned the state psi prime into a copy of psi. And that's the form of the procedure, which is called teleportation procedure. Well, this is one of the more colorful examples of quantum information work, a very nice one, in which you can visualize the entire thing using the tensor network like this. And the entanglement is being represented by a graphical connection from one end to the other, you see? So already when you're doing this kind of representation, you use graphical connections between the non-local places in which the entangled states occur. So it is just a truism about using tensor networks that to every entangled state, there corresponds a graphical edge connecting one site to the other. Well, we could take that seriously if we want to build in the direction of Susskind. And I don't think I need to show you the rest of these slides. This slide has everything in it. We could use that as a beginning and ask, well, why not change the topological space by adding the network to it? So that's what I want to do. So I say that in working with tensor networks for quantum systems, we use graphical connection to indicate quantum entanglement. Why not formalize the relationship? What would that look like? Well, I want to do it in a minimal way. So I have here a space, some topological space, like ordinary 3 space. And I have a couple of points, L and R. That's Chicago. L stands for Chicago and R stands for London. And an entangled state with its left tensor end and its right tensor end, available for observation in London and in Chicago. And I've indicated it by the usual graphical edge of a tensor network. I want to make a topological space out of the entire arrangement. Well, you could do it a little differently, but once that idea is there, you could do it. I'll do it this way. I'm going to add this point E. I'm adding 1 point for the edge. 1 new point to the original topological space. And then I have to tell you what the neighborhood of this point is. And the neighborhood of this point consists in a neighborhood in the original space, U of L, union the point, union a neighborhood of the other end, U of R. That's a least neighborhood of E. You can choose any neighborhood of L, any neighborhood of R, and put E in it, and that's a neighborhood of E. So there is no neighborhood of E that does not connect L and R. It's a non-Hausdorff topology, but nice and minimal. I'm not adding infinitely many points along the graphical edge. The graphical edge has been abstracted back into abstract graph. It's just a point, but that point is now non-locally connected to L and R. And I need those neighborhoods because I want to make the new space connected, even if L and R were disconnected. But you will notice some little points about topology that would occur. If I only took L and R and E and called that the open neighborhood, then I could take the complement of L and R up there in the space union, the neighborhood of E, and those would be 2 disjoint open sets that formed S. So I would lose the connectivity of the space if I didn't take a little bit of neighborhood from the space. So that's the construction for the augmented space. And the network itself, you can generalize this topology on a network to an arbitrary network, and then you plug it into the space by taking neighborhoods in the space like that and form a new space. The new space now has lots of little quantum wormholes going between any 2 points of entanglement. But of course, they're not differential geometrical wormholes. They're just the tensor net that describe the entanglement. So that's my small mathematical idea that I'm exploring. Now let's think about connectivity a little bit. A topological space is connected means that it is not the union of 2 disjoint open sets. If you're given so I take the following remarks to be interesting to me anyway. If I have a topological space, let H of X be the collection of open sets in it. So if I have U in H, then I'm going to define tilde U to be the interior of X minus U, a very nice definition of a tilde, a kind of negation. Tilde defines a Heyting algebra negation on H. In general, you have that tilde U, union U, is not equal to X. Think about it. You're taking the interior of X minus U. So if there is a frontier, the frontier will be left out, and tilde U, union U, will not be equal to X. For example, suppose I have an interval space from 0 to 1, and I take the half-open interval to 1/2 as U, and V will be the half-open interval from 1/2 to 1. Well, tilde U is V because the complement of U, it includes the boundary point 1/2, and that frontier is dropped out, and you get the half-open interval. So the union of U and V is equal to X minus the frontier. Connectivity is directly related with having non-Boolean hiding. And in the hiding situation, I'm not giving you all the axioms for hiding algebra, but it looks like a Boolean algebra with a different kind of negation, you see. If you take W to be equal to U union V, that's the whole space minus the 0.1/2, the connector between those two. If you take W to be U union V, and you see that tilde W is empty, because tilde W is the frontier of a point, which is empty. It removes the frontier. Tilde U, therefore, is the whole space and is not equal to W. But tilde W is empty, and that's the same as tilde W. It's characteristic of hiding situations that a triple negation is equal to a single negation. So all the while you've been working with connected topological spaces, you've been working with a non-standard Boolean structure, hiding algebra structure. And when you have a totally disconnected topological space, then you're looking at a Boolean algebra. So when I do this kind of construction that I'm doing of adding one point, I'm making a little bit of a non-trivial hiding negation happen. So we have the following summary of what I've been saying, that topological connectivity corresponds to non-Boolean hiding structures, and it can correspond to quantum non-locality if you used the network description of the quantum non-locality and made a topological space out of it. That would be a minimal way to get topological connectivity related to quantum non-locality. And then that says that quantum non-locality is related to the hiding structures. And there might be more along that line, I suspect. So those are my speculations. Of course, you'd like to think about more articulated kinds of connection rather than just an abstract connector like I made, things like wormhole tubes going from one to another. And in thinking about that, it's probably worth reminding ourselves that when we think in terms of topological quantum field theory, we let cobordisms go over to things which are much simpler, linear mapping, so that if you had a cobordism like a wormhole, well, then you could think of it as going from the vacuum upward into the tensor product of the spaces associated with the ends. And then that corresponds to a vector in V tensor V, and it may well be an entangled state. So there are natural ways to think of entangled states in relation to wormholes along those lines. And so there's a project there to examine relationships of manifold topology with the fundamental relationship of non-locality and entanglement and connectivity. So one more example, and then we'll stop. You could have, here we have Chicago, London, Paris. And in London, the right end of this entangled state is next to the left end of this one. And in London, we could make a measurement. When we make a measurement, you see from this description that we're changing the topology. So that's interesting and should be followed up, that when you make a measurement, you change the topology of the augmented space so that measurement and change of topology are related. That's an idea that was suggested by Aravind in a different context, which we could go into if we weren't stopping. And in any case, this is a bit of something that is interesting from the quantum information point of view. Two entangled states that have a local meeting could, through a measurement, become a longer range entanglement. So now, if M is a good choice of measurement, then we have a longer range entanglement from Chicago all the way over to Paris, and that's called entanglement swapping. There's another state that can occur in the swap, which I didn't draw. So that's interesting. And here I'm just describing, if you get the notes or a paper later, you'll see, I'm just describing how I would put a topology in a simple way on a network itself, but we won't worry about that. Another thing you could think about is if you had a matrix in here in the net, which was a projector, then you can keep putting many, many copies of that matrix, and the topology will change as you put more and more copies. You'll be putting more and more points. So while this is equal algebraically, the topology will be acquiring more and more points, and you could think of taking limits under those situations. So we've shown how to augment a space to a new space that contains a topological version of the tensor networks describing its quantum structure. This marks the beginning of a possible unification of properties of spatial connectivity and properties of quantum entanglement. And I thank you.
Well, thank you, Lou. That was mind-blowing. Yeah, I think so. Are there any questions? I mean, there's a lot of...
Looks like there were a number of things happening in the chat. I didn't watch them.
No, well, that's all recorded, so yeah.
Okay, good. On Thursday at noon, Chicago time, we're listening to that a recording of Leonard Susskind talking about this. Yeah. You don't have to come to that, but you're welcome. And if you do want to attend it and you don't happen to be on the list for the quantum topology seminar, send me an email and I'll put you on the list. Otherwise, if it doesn't meet your times or requirements, I do recommend finding Susskind's lectures on the internet about these things, because it's really interesting to listen to him talk. He's wrestling with problems of principle about quantum information and black holes, and there are no calculations. There's just reasoning and a lot of thought.
I think I have a couple of comments. When I saw the cubes, I first thought about the paper, the work of Kuperberg, where he was talking about hexagon tilings by cubes and their relations to physics and to knot theory and to everything. So when you were talking about two possible cubes in two directions, so possibly this can be related to Kuperberg. This is one comment. And
so wait, stop for a moment. So is the key word for getting his paper hexagon tilings? If I look him up on the archive for that, there'll be a title that says something about hexagon tilings.
I think so.
Mm-hmm.
And one more question. Yeah. And one more question is, independence, independence or no correlation or no entanglement seems to be very similar to some orthogonality and some commutativity. Well, usually I think of everything in terms of groups. So possibly some entanglement should mean that some generators do not commute, and non-entanglement should mean that some generators do commute. I wonder whether there is any group theory language of that.
That could be that there's a formulation that way. The usual formulation is that two states are regarded as unentangled. If you put them together, you take their tensor product. So if a state falls into a tensor product of two states, then it's said to be unentangled. And if a state is not a tensor product, like 0 tensor 1 plus 1 tensor 0 is not a tensor product of two one-dimensionals, then it's said to be entangled. So the usual point of view has to do with decomposition of tensor products.
Okay.
Mm-hmm. But what you say may be related to it as well.
Well, usually if we have tensor products, then we can get presentations of something in certain spaces. So it's easy to find a representation of groups when something commutes. It will be a tensor product. And if something does not, it would be a more complicated representation.
Well, we can talk about that further. Sure.
I mean, I'm wondering if the check complex obtained from your open sets, I mean, is that just a path in that check complex or something? Does that make sense? Joining the two states.
You want to take the nerve of the coverings that I make there, and then that's a good idea. Take the nerve of the coverings that I make there and ask for the check homology of the space, or try to understand it that way. Yeah. Mm-hmm.
I mean, is there some connection between this Heiting algebra and the geometric algebra, which
well, they both have the term algebra, so we're getting there.
So right. That's a start.
Okay. But there might be. There's a physicist I knew, David Finkelstein, who kept trying to formulate what he called quantum set theory. And in his formulations, because he respected Clifford algebra so much, he basically had Clifford algebra down at the bottom, right along with the first set, in his way of thinking. If you had a quantum set, it had a Clifford algebra structure associated with it.
Oh, okay. Well, that's something to explore, certainly.
Yeah.
So at one point during my daydreaming during your talk, I was struck with.
Thank you. That's what you were supposed to do, right?
Yeah, Madeline Engel and A Wrinkle in Time, and the quantum entanglement has something to do with the state that Charles Wallace finds himself in. So I think that there's more of a metaphor there than
what state did Charles Wallace find himself in?
Well, it's been a long time since I've read the novel, so I've only watched the movie recently, and he seems to have been co-opted by a devil-like character at some point. But the Wrinkle in Time, I think that she got the metaphor wrong by using a tesseract rather than a wormhole.
Okay, well, so that's required reading for next time. Madeline Engel's book, A Wrinkle in Time.
Yeah.
Well, the only thing I know is that these wormholes are going to be totally useless. You can't just jump into them and go from one side of space to the other.
Alas, that's probably true. The amazing thing about the teleportation procedure is that people were being very frustrated before that was invented, because they thought, well, entanglement states ought to let us signal faster than light from one point to another, but the randomness gets in the way. And people made various proposals for communicating faster than light, all of which failed. But what Bennett and his collaborator figured out, Bennett and Belisard figured out, was that if they would just do the measurement in Chicago and then send a tiny bit of classical information over to London, that was enough to affect the whole procedure. So while you couldn't go faster than light, you could do something very efficient. So this suggests that maybe wormholes would be useful after all.
Oh, okay.
With some extra bit of work.
Yeah. Okay. Well, I can hear somebody with a radio on in the background. Never mind.
I have one question.
Can everybody mute if they're not talking? Is that possible?
Yeah, please mute your microphone if you're not of the question asking.
Okay.
Yeah, Sammy?
Hi. I was
Hi.
wondering.
Good to see you, by the way. I meant to respond to an email you wrote me a month or two ago, and I forgot. So, hello. I'll get back to
Hello,
your
nice to
email.
see you. Thanks. I'll write or ask again. If what I wanted to ask is there two particles being entangled? Is that is that property preserved under time always, or can things become tangled and then untangled later, or what are the
Well, what happens in time to a quantum state is that it interacts with its environment. If it didn't interact with its environment, that would then it would the structure would remain the same. But the chance of a quantum state interacting with its environment is always very, very high. So, in the course of time, the entanglement would disappear. Lots of things would change. So you have to have some protection. That's always been the problem in making a really good quantum computer, is that you may set up the quantum states to have a good property, but then they interact with their environment and decohere and are no longer any good for you. So things have to happen as quickly as possible, and you have to correct for those errors.
Okay.
I'm speaking from a computing side, but you see what I mean, right?
Yes, yeah.
Now, I suppose that if you have something like a humongous black hole, which is supposed to be your entanglement, then it would be very impervious to perturbation, right? It's not going to disappear. But if you go back to Physics Girl, you'll notice that she did some experiment in there where she went in and interfered with the hole, right? I mean, she interfered with the connection, and it goes away, and the vortices disappear, right? So even in that macroscopic experiment, something had to be protected from its environment in order to persist.
Right. I mean, in that experiment or otherwise, so there seems to be some problem with transitivity of entanglement, so to speak, right?
Transitivity, did you say?
Yes. If A is tangled to B and then B is tangled to C later, does that imply A is entangled to C now? Or in the case of in the beginning of the talk, you were referring to quantum monogamy or some restriction.
So if you have A, B, and C, and B is supposed to be entangled with both A and C, that will make it difficult for they could all. There are examples where you see that sharing causes some difficulties.
Okay.
An example would be this one. I don't want to try to make more complicated examples. I'm incompetent at this point, but consider this example. This is a wonderful, famous example, which is in the trade called the GHZ state after Greenhorn and Zeilberger, who were studying it. Oh, I'm sorry. I'm trying to write in the chat line unsuccessfully. There's the GHZ state in the chat line. Now that's 3 particles. And they're entangled triply. But not in pairs, not in pairs. They're just like the Borromean rings. If you were to observe that in one of its factors, then you end up with 0, 0 or 1, 1, which are unentangled. So this is a quantum Borromean rings.
Okay, that's interesting.
I should mention that in the paper with Stathis and Sophia, we make the remark that I made about the cobordism, and we make that remark actually not very originally, because, for example, Bias and a collaborator wrote a paper about EPR and categories in which they make the same remark a few years ago. But in the paper with Stathis and Sophia, we are thinking about the geometry and topology of the black holes and wondering about surgery in relation to them. And so we can ask a lot of questions about how would this entanglement that would be associated with a black hole fare in relation to surgery on the three manifolds. And we don't answer that question, but that question is hovering over what we were doing in those papers. So we wrote some papers which are we hope a good beginning toward thinking about surgery in black holes, and may well help us talk to people who also think about that. Does that comment of mine help, Sophia? You might want to say something else.
No, that's all. Thank you. Very nice. I think we tried to make the conjecture that given the ER equals EPR hypothesis, that there may be surgery happening in the black hole, three-manifold surgery instead of, what is called criticality, let's say. So,
right. So you can ask what kind of effect would surgery have on the quantum states?
Exactly. And we try to conjecture on this. So maybe Stathis could present this work in the seminar. Perhaps.
That would be great if Stathis is interested in presenting to this seminar.
Yeah, I don't see him in. He was on Tuesday. He was in the Chicago quantum topology seminar, but we can tell him.
We can twist his arm.
Agrees.
If you send his email, I will contact him, or maybe we both can.
Surely. Okay, thank you.
Okay.
Thank you, Sophia. Getting back to the GHZ, the GHZ was grabbed by a physicist named Aravind, who's a very good quantum physicist, and he wrote a little paper which continues to strike people's imagination, in which he said, yeah, the GHZ really does look like the Borromean rings, and his paper draws a picture of the Borromean rings. And then he said, and measuring the GHZ means looking in one of the tensor factors and dropping it, right? And it becomes unentangled. And so measuring the Borromean rings should be what? Here's the Borromean rings, and you're going to measure an analogy to quantum theory. Oh, cut one of the rings. And then the other two fall apart. So there ought to be some play between linked rings, links, and quantum measurement, where a measurement on the topological side would be to change the topology by dropping a ring. So as I said, in my picture, changing of topology does correspond to measurement, but I haven't unified the Aravind idea of dropping a ring with the kind of change of topology that I was talking about here. And this usually, if you walk these lines, you end up realizing, oh, well, I'm behaving like a topologist and following an idea, but it veered from really being quantum theory at some point, and so I have to backtrack. Or maybe I got a good idea in topology and I'll forget the rest. It keeps happening to us when we try to do this. For example, Sam and I, years ago, started talking about quantum knots using mosaics. And the mosaics are much more popular than the knots. A lot of people think about mosaics now for representing knots. Not just grid diagrams, but mosaics where you draw bits of knot in little squares. And that's a nice image. And almost nobody really tries to make them quantum, alas, but that's still possible.
Well, I think I ought to bring the discussions to a close now. And I would like to thank Lou very much for a fascinating and invigorating and so claps all round.
Thank you.
Okay, and I will send details of next week's talk if I can sort one out. Okay, bye for now.
Bye.
Bye.